So thanks very much for the invitation to be here. I titled my talk, Echoes of Entanglement from Quantum Metrology to Black Hole Scrambling. And, you know, I was actually asked the question yesterday, why are you here? Aren't you more of a many-body quantum physics person than a cosmology person? And the accusation is true. But let's see, the slide is actually very dim. Just checking that. Is it the, yeah. I'm just worried that okay, I think it will be fine. Good. So, no, it's just, this is a Venn diagram. So there's a blue ellipse here that you can envision, and there's a yellow one here. And the argument I wanted to make is that quantum many-body physics can potentially contribute to cosmology from two different directions. So one is I've been enjoying hearing over the past 2 days about many ways in which atomic precision measurements can be relevant to detecting anything from dark matter to gravitational waves. And one question I'm interested in is what we can do in the way of engineering many particle entangled states that can advance the capabilities of those measurements. And on the flip side, what we might be able to do, though, in terms of engineering systems in the lab that could simulate cosmological phenomena, such as potentially black holes. And so the sort of model system in particular, in terms of engineering new kinds of interactions to enable new capabilities, the model system I'll be talking about is one where many atoms, cold atoms, are interacting via a rather new kind of interaction, a light-mediated interaction in an optical cavity. And there are a couple of nice features of this interaction. One key one being that it's non-local. And so it's a way of having many atoms become entangled sort of en masse in a way to generate states that could be useful for quantum-enhanced measurements. And the second kind of unique feature of these non-local interactions is that they actually arise in models that are of interest for thinking about quantum information in black holes. And so in my talk, I'll start with the quantum metrology angle, and that will also give me an excuse to introduce the type of experimental system I have in mind with these long-range light-mediated interactions. I'll talk about some ideas for pushing precision measurements towards the fundamental Heisenberg limit, and then I'll transition to talking about the quantum simulation angle. So, we've heard a number of talks that I've been particularly excited to hear a few talks about using optical clocks for precision measurements of cosmological phenomena, using optical clocks and taking advantage of their exquisite sensitivity to use them not just for timekeeping, but for sensing. And so this is particularly a direction where we can start to ask the question, if we have a fixed number of particles limited by the size of my lattice and limitations of collisional shifts that we heard about that constrain my particle number, if I'd like to get the best possible precision under those limitations in a fixed time, that's one place where entanglement has the capability to help. Beyond that, we heard ideas for instance, resonant detection to enable searches in particular frequency ranges. And so the sort of second point I'd like to make is that besides sort of entanglement being a way to enhance measurement precision with a fixed number of particles, it's also potentially a way to reach a fixed precision with fewer particles, and then one can think about, can I have some kind of a sensor that maybe it consists of multiple ensembles where I'm winning in bandwidth by interrogating different frequency ranges in parallel, for instance. So these are some directions where entanglement can help. Okay, and if you saw Mark Kasovich's colloquium yesterday, you've already heard about some examples of actually engineering useful entangled states in the lab. And so Mark showed you some beautiful experiments using squeezed spin states to enhance an atomic clock. So, and I draw this picture here of Ramsey spectroscopy with a squeezed spin state because I'll use this same type of picture of some quantum state on a sphere throughout this talk. And so just to be clear, whenever I show this type of picture, I'm basically thinking of some ensemble of n atoms, and this sort of red blob is indicating, well, both the mean spin of that collection of atoms, but also the quantum uncertainty associated with where it's pointing. And one of the developments over the past few years has been the ability to kind of redistribute that quantum uncertainty by entanglement. So this was an experiment we did a few years ago in Vladen's lab at MIT, where the short-term stability of an atomic clock was, in that case, improved in such a way as to reach a fixed precision 3 times faster. And now, just recently in Mark Kasovich's lab, this has been pushed to the level of reaching a given stability 10 times faster, and there's room to improve that further. So that's really one example of applying entanglement to enhance a precision measurement. And this is sort of a collection of various experiments that have been done in this direction in various labs around the world. The 2 bold ones are 2 examples of, in this case, both microwave atomic clocks. And there are a couple of points I want to take from this plot. One, so this is, the x-axis is just the number of particles that was involved in the measurement. The vertical axis is the metrological gain due to entanglement. Absolute precision, the yellow lines are sort of lines of constant absolute precision. So if you want to push up your precision, you'd like, on the one hand, to, there's sort of the classical route, which is using more and more and more particles. And once you run into some limitation, you can go up on the plot by entangling them. Okay, so this is one direction that's certainly interesting. This, again, was that recent experiment in Mark's lab that is really pushing both particle number and metrological gain to win on both axes. And another direction, though, that I'm also quite interested in is even asking the question, can we achieve the same precision with fewer particles? And then, for instance, that can be a starting point for using those, say, multiple ensembles in parallel to do more than you can with a single one in terms of either enhancing bandwidth or potentially enhancing the dynamic range of a sensor. And this has also been shown to be useful for really reaching fundamental bounds on the short-term stability of an atomic clock, which is great if you want to use it as a sensor. Okay, so with that in mind, the question that comes to my mind is, well, this is the standard quantum limit. This is the best I can do without entanglement. All of these results are still very far from this fundamental Heisenberg limit, which would be essentially a phase resolution that goes as 1 over the number of particles. So are there things we can do to push in this direction? Okay, well, that limit really comes about, in the case of a clock, from the energy-time uncertainty principle, right? If I want to reach that limit, I need some state with a maximum uncertainty and energy. Okay, and so if I'm dealing with 2-level atoms, spin up, spin down, that's that maximum uncertainty state. That's a Schrodinger cat state. Okay, superposition of alive and dead. And so intuitively, that's hard to make. So I want to ask kind of a couple questions. How might one approach making these kinds of states at larger and larger particle numbers? But also, are there easier alternatives that are sort of more realistic and can nevertheless get us towards this limit, if not precisely there? Okay, so in terms of thinking about how one might make these kinds of states, I can start by sort of thinking about the classic Gedanken experiment from Schrödinger himself. First thinking about this, right? It's a cat in the box, and some radioactive particle might or might not decay and kill the cat. And in some sense, actually, a cavity QED system is the closest analog I can imagine to that. The box is a pair of mirrors. The cat is some ensemble of atoms. And my radioactive particle might be another atom I can separately address. It may or may not, depending whether it's excited, emit a photon into the resonator and have some macroscopic influence on the ensemble. And so this is why kind of the cavity QED system is one natural system for trying to think about engineering these types of very non-classical states. Okay, so that's one direction that we're potentially intrigued by trying to pursue in my lab. But a second direction that I should mention, and one that's actually been demonstrated to make these Schrödinger cat-type states in systems of a few ions, is having actually not one particle interacting with many, but just a collective interaction of some group of spins. So that, in particular, so the kind of Hamiltonian one needs is something that looks like this. So the non-interacting system would just be a Hamiltonian SZ. This is a Hamiltonian SZ squared. And what it does basically is take this sort of quasi-probability and twist it about the z-axis. So the lowest order effect of that is spin squeezing, and that's been used to generate those dynamics. And in principle, if this happens coherently long enough, one gets interferences that eventually give rise to something. Here's looking at the front and the back of the sphere. That's a macroscopic superposition of two orientations. So that's been done in small ion chains. And you can sort of see it requires very coherent dynamics for a very long time. Okay, so these types of dynamics for generating cat states, it's been done in ion traps. More generally, these types of interactions have been realized in BECs and in cavity QED systems to give rise to spin squeezing. And so my focus today is on light-mediated interactions. So let me actually just give you an intuition for how one actually gets these types of collective spin interactions mediated by light. So the picture you can have in mind is something where I have some atoms trapped in an optical resonator. I send in some light from the side, and any particular atom could scatter a photon into the resonator and in that process flip its spin. And if another atom rescatters that photon flipping its spin, that can generate some sort of correlated spin flip processes, which might look like flipping both up or both down, one up, one down. If I add up all the possible terms, I get an interaction that looks like SXI, SXJ, for between the spins I and J. Okay. And so in principle, actually, this is a very versatile technique in the sense that if I can address these atoms, I can have control over arbitrary pairs of the spins. If I simply address them all in the same way, this would give rise to the collective interaction I showed on the previous slide. Okay. It's actually, unlike sort of most types of interactions we have in nature, this is one where I can actually quite easily change the sign. Is it ferromagnetic or antiferromagnetic? That will be an important point. And it's simply controlled by the detuning of some laser. Okay, and then in the limit, the last point is this can be, in principle, a very coherent interaction in the limit where the atom-like coupling is strong compared to the characteristic decay rates of the system. And so the key figure of, there's sort of a key figure of merit here that's called the single atom cooperativity that's saying how strong, what is that coupling to decay ratio. Okay, so, and in the limit where that ratio is strong, the process where a photon goes into the cavity can be off-resonant and sort of a virtual process, and I don't suffer from loss. Okay. So that's kind of the desirable parameter regime to be in. I should say that this approach to generating spin-spin interactions, I briefly said it before, has been demonstrated, not yet in that strong coupling regime, in a slightly different scheme, but it's essentially the same physics. So these were data from MIT a few years ago. And the key thing I want to point out, so this is basically, we've applied some amount of light. The various curves have some many-body system, in this case maybe a spin chain. And I have two operators that are just, say, simple spin rotations that commute if I perform them at equal times. So rotating this spin, rotating that spin. So the question is actually, now if I let this system interact, then the influence of this rotation here will eventually spread to affect that spin. And so then we can ask the question, if I do these two operations at different times, do they still commute? Or do they fail to commute due to the interactions? And so the time scale for scrambling is actually indicated by the rate at which operators like this fail to commute. So how fast do these, does the commutator grow? Okay, so if you'd like to be able to measure this, what you'd like to do is essentially have some initial state and compare two possibilities. One is I apply this operation V, and then I let the system evolve under some interactions, and at a later time I apply this operation W. Or I let the system evolve for some time t, I apply the operation W, and then I go back in time and apply V at an earlier time, right? I'd like to ask about this commutator between V at initial time and W at a later time. So just sort of maybe another way to think about this is the kind of upper possibility here would be the case where I gave this talk with all of the slides in exactly the right order, and you're happy because you understood everything I said, right? The lower branch is something where I accidentally actually skipped some slide early in the talk that contained a crucial piece of information. And I sort of went on talking, and then I realized I missed that piece of information, and I started to flip back, and then I gave you that slide. Okay, so, if this happened with only, one slide in between, it might not be so bad. You would still be pretty happy here. But if I go through the entire talk and then realized I missed something crucial on the first slide and flipped all the way back, you'd be pretty confused. Okay. And so at the end, what I basically am trying to do is kind of measure the overlap between the happy you and the confused you from applying these in the right or the wrong order. Okay, so if I'd like to do that, essentially this looks like some kind of an interferometer, right? So there are kind of two ingredients I need. I need some sort of way of interfering these two many-body states, and I need a way of going backwards and forwards in time, which is switching the sign of my Hamiltonian. So those were the natural set of tools we thought of. I should mention there have been a couple of alternatives, one suggested by Eugene and others at Harvard. And yeah, so there are a couple of other proposals, but I'll focus on this approach, where the tools I'll need are time reversal and some many-body interferometry. Okay, and so in order to perform this kind of interferometry on a many-body state, the essential approach then will be to have a single qubit that acts as a control. And so that this can be some spin, and if it's in a state that I'll call 1, then it will perform, I'll use it to perform this operation V. If it's in the state 0, it'll do nothing. And then at some later time, I'll do a pi pulse on that qubit, and that will allow me to perform the operation kind of in the lower branch of the interferometer. And if after all of this, I perform a measurement of this qubit in the x or y basis, that will actually directly give me the overlap between these two possible orders of performing the operations. I didn't say it before, but this overlap then, I'll call it f of t. This thing is called an out-of-time order correlation function because of the weird ordering of the operators here that are performed at t equals 0 and some later time. Okay, so there are a couple of different, specific choices you could make in terms of the operations you're measuring this with. This is, but the typical time scale for these correlations to decay will be our signature of scrambling. And so in the picture I showed before, I showed some local operations where I'm flipping a spin here, flipping a spin there. It could also be some global operations on a many-body system that are small in some other sense, so small collective spin rotations. That's actually, I'll give an example involving global operations. And I'll give that because it will allow me to kind of give you some way of kind of visualizing what's going on in this scrambling process in a collective spin model that I can draw on this block sphere picture I've been using throughout the talk. It'll also give me a way of analyzing a little bit, can this type of procedure be robust to realistic dissipation in any real experiment? Okay, so the cavity QED setup, as I explained earlier, is kind of a natural way of doing some qubit-controlled operation on an ensemble. And so I'm envisioning here some control qubit that can perform a controlled rotation on all of these ensemble spins, and in addition, the possibilities to separately address this ensemble to generate interactions within it. Okay, and the particular type of interaction we'll generate is a paradigmatic model for chaos that's called the kicked top. And so I chose this one because it involves just these collective spin interactions that we know how to engineer, and some spin precession, which are both ingredients that are straightforward to realize experimentally. And so essentially this is a model where one has stroboscopic alternation between applying interactions and applying this spin precession. It's a little bit analogous to a kicked rotor, which some of you may be more familiar with. Okay, and this is well studied, and one thing that's known is that in order, if I start with some coherent spin state, then the number of kicks that are needed for this to spread over the entire sphere is on the order of the log of the number of spins, or the log of the total spin here. And there's kind of an intuition for that, which is coming from the fact that my initial unentangled state had a solid angle 1 over n, right? 1 over root n by 1 over root n. It's the area on the sphere. And so roughly speaking, if there's kind of a butterfly effect on that sphere, I would expect that to need to grow by a factor of n in area, and that should take log n kicks if the growth is exponential. Okay, so what happens if we look at the out-of-time order correlator in this model by probing it with some small collective spin rotations that are on the order of the quantum noise of the initial state. Okay, so here's a numerical simulation, and the yellow I'm showing here is actually a reference curve showing a time-ordered correlation function. That's more like that Low-Schmidt echo, just evolve forward and back in time with some perturbation in between. And this is the lighter and lighter curves are for larger and larger atom number. Okay, and what one sees, there's some kind of a fast decay. It's actually, sorry, lighter curves are for smaller atom number. So it's a little bit faster the more atoms you have, which might not be so surprising. Interestingly, if one looks actually at this out-of-time order correlation function that's probing the scrambling, what one sees is a time scale for the decay that actually gets longer and longer the more atoms there are. And this matches this notion of this scrambling time scaling with, depending on the number of degrees of freedom in the system, scaling with the entropy. Okay. And in particular, this seems consistent with a growth that's the log of the number of degrees of freedom. Okay, so this matches what we'd expect from some kind of a butterfly effect. And you can ask the question, is this something actually realistic to look at in experiments? And roughly speaking, for this exponential growth, we can estimate sort of how strong does the single atom cooperativity need to be in a cavity setup to see this. Okay, and it's something that scales as log of the atom number squared. And we plotted here what you actually would expect to see if you did this not with perfect unitary dynamics, but with a single atom cooperativity of 100, where there's a little bit of dissipation. Okay, and qualitatively, it looks like one can clearly distinguish the time scales for this time-ordered and the out-of-time ordered correlators to decay. And in fact, I should say that I was actually curious to see what happens if the dissipation is worse, and this actually becomes hard to calculate. And so at some point, okay, one has to do the experiment. But what I like about this upper plot is it tells me there's actually sort of a really interesting signature that is that if I observe something where this time scale is actually growing with the number of degrees of freedom, that's really something that's quite unique to this scrambling, and it's not something that I would expect from some decay that's just due to some dissipation in the system. Okay, so the sort of key points I want you to take from this are, first of all, this is fundamentally interesting in being a sort of really a fundamental time scale for many body dynamics that I wanted to say has yet to be probed in any experiment. There are actually 2 experiments in the archive in the past week or so, starting to look at these types of correlation functions in either ion traps or NMR systems. But there's still lots to do in terms of questions to investigate here. Key signature to look for is this sort of slower decay of the out-of-time correlator, the more degrees of freedom there are in the system. And in particular, I showed this in sort of a toy model, a chaotic, globally interacting model, but this becomes interesting in models with a more sort of a richer structure of non-local interactions. So one can think about implementing something like this random circuit model I showed before with random non-local interactions that gives rise to something similar to this fast scrambling. And in particular, though, what's interesting is that models with non-local interactions, so the random circuit model is a little bit unusual in that it's a time-dependent model. But more generally, models with some static non-local interactions are the types of models that have been shown to saturate that fast scrambling bound, suggesting that they're, in fact, holographic jewels of black holes. Okay, so there's also lots that can actually be done in terms of looking at local Hamiltonians, but I see Paula standing up, and so I won't say anything about that, except to just summarize and say that this sort of type of time reversal is really interesting sort of from 2 angles. On the one hand, gives us a way of accessing entanglement that would otherwise be hard to access and using it for precision measurements. On the flip side, as a new way of quantifying many-body quantum chaos and probing dynamics that ultimately may tell us something about the scrambling of quantum information in black holes. So finally, I'll just summarize by thanking my graduate students, Emily and Greg in particular, in the cavity experiment, and Brian Swingle, my collaborator in this scrambling work. Holger, yeah.
Special tricks in stabilizing the cavity?
Special tricks in stabilizing the cavity.
Because
The aspect that it's very sensitive to yeah, so I should say it's not degenerate, actually. It's near concentric, but not quite concentric. It is still, as you said, very sensitive to misalignments. So far, it seems to us that the passive stability is fine. At something like a 11 micron waist is where we've been able to sort of stably align it. Where we're still in the process of getting all of the lasers locked to actually do physics with it, so maybe we'll learn new things. But we don't have special tricks yet, yeah. Except that, as I said, we have the ability to align it in vacuum after baking. We have baked it and realigned it, and that was certainly necessary to have actually 5 degrees of freedom, namely the tip and tilt of each mirror and the length.
Great, but so far so good.
So far so good,
Great.
yeah.
For this scrambling experiment, you mentioned that when you add too much decoherence, it becomes difficult to calculate.
Oh, yeah.
But is the current experimental regime in the regime where you can calculate things or beyond that?
Yeah, so the calculation there was within a factor of 2 of the current experimental parameters. So.
It should not change faster.
Yeah, I think in some sense to me it's interesting that to actually work in a regime where things are hard to calculate. And ultimately that's, I think, where experiments should go. And so also these, once the reason this collective model is simple is that the Hilbert space is actually only, the dimension only scales as n instead of 2 to the n, right? And so really what's particularly interesting is looking at strongly correlated systems in an exponentially large Hilbert space, and can one do some quantum simulation that will tell you something that you can't calculate. And sorry, one other point I'll actually add to that is the systems that are holographically dual to black holes, that duality gives people a way of calculating things. And then so in some sense there's an interesting question about what about strongly correlated systems that can't be studied by taking advantage of that duality. So.
I guess that everybody wants coffee.
Okay.